Hi guys, welcome to the second video in the series on how to do ICE charts. This will be the moderate level ICE chart. You can take a moment to copy down the reaction or the problem that I have that I'm displaying right now. What I've done to kind of make the video go a little bit quicker, I have actually already written down the reaction, all the molar masses, and the starting quantities in grams there. So if you want to pause the video, you can take a minute and try to do all that stuff yourself before we move on. I have yet to balance it or to fill out any of the rest of the ICE chart. Okay, so let's get started. So here's the reaction in the ICE chart. I have included already the molar masses up here. Now I have rounded the molar masses to the nearest whole number. You, as the student, shall take those numbers and you shall find them on the periodic table and not round them. And I've also included the masses of the starting materials, like I had already said. So now the first thing that we should do is balance the chemical equation. So it doesn't matter what we start with. I'm going to start with sodium here. There's one sodium here and 3 sodiums on this side of the equation. So I'm going to put a 3. Now, the number of nitrates here is 3. Remember, this 3 is part of the nitrate, so we don't count that 3. So it's 3 nitrates. And then over here, there's 2 nitrates. And so the thing that happens is that we need 2 and 3 to equal each other. So the least common multiple between 2 and 3 is 6. So we're going to put a 3 here. 3 times 2 makes 6 nitrates, and we're going to change this to a 6. But by changing that, now we have 6 sodiums, and now we need to change the number of sodiums over here. So we have 3 already, so we need 2 sodiums in that reaction. And by doing that, that balances the whole equation. Now, some of the things that we can do before we get started, before we start doing any math, we can always put zeros here. Well, maybe not always, but most of the time we can put zeros here, because when we have products, we usually never start with products. Initially, we don't have any products, because why would we do the chemical reaction if we already had some of the products, some of the things that we were trying to make? So we typically start with 0 products. And now we can also, for the change column, we can subtract from the reactants. That's what this is, because reactants are used up in a chemical reaction. Their change is that they're going to be subtracted from the initial amount, and then we can add products. Okay, so we can fill in a lot of this to begin with. Now, when we do chemistry on a paper, like I'm doing here, keep in mind that we need to make sure we convert to moles. So when we do this, we're going to convert to moles by using the molar mass. We X-line it using the molar mass. So let's see, I'm going to do some dark green work in here. I'll take this and we will do the math right here. So here's what we do: 13.6 grams of NaNO3, sodium nitrate. X-line. Now that's the thing that's going on here. The X-line is the thing that's going to help us the most. Okay, we want to get rid of grams, so we're going to put grams on the bottom. And then we want to convert it to moles, so we put moles on top. For every 1 mole, there's 85 grams of sodium nitrate. We do that math and we get 0.160 moles of sodium nitrate. Okay. Now we have to calculate the same thing, number of moles of calcium phosphate. So we have 8.93 grams of calcium phosphate. And again, we're going to X-line it. What are we trying to get rid of? Grams. What are we trying to convert to? Moles. And so for every 1 mole of calcium phosphate, the mass is 310 grams. Now we look, grams cancel, leaving us moles of calcium phosphate. So our answer is 0.0288 moles of Ca3PO4 2. Sorry, ran out of room a little bit. See? Oh, perfect. Okay, so now we come back over to our ICE chart, and guess what we can do? We have now successfully converted that to moles and that to moles. Remember, I say this all the time. When we do chemistry on paper, we have to do it in moles. When we do it in the lab, we're going to do it in grams. So since we're doing chemistry on paper, here we go. So it's 0.160 moles and 0.0288 moles. Now, I'm doing a little shortcut here because I'm not putting the units in there. Whenever we have an ICE chart, we just assume that the units are moles, and so that's okay. And then also notice I'm carrying through my 3 significant figures all the way through my ICE chart. Okay, so now we have to calculate the limiting reactant. Now, the limiting reactant, we can't just take the smallest value. That's incorrect. Do not do that. Okay, what we have to do is we have to take what I call the stoichiometrically smallest value. So that means we have to take the amount that we start with and divide it by the coefficient. Same thing here, the amount we start with and divide it by the coefficient. So I'm going to set that up. So I'm going to separate the limiting reactant calculation. I'm going to put LR here for limiting reactant. Then I'm going to say for sodium nitrate, NaNO3, that's going to be 0.160 divided by 6. I don't even care about units in this case, okay? Because the limiting reactant, it's all going to work itself out. And then for calcium phosphate, CaPO4, 2, calcium phosphate, this is going to be 0.0288 divided by 1. Now when we do the math, the answer here, this answer is 0.0266, and this one is obviously 0.0288. Now, we pick which one is the smallest. This guy is the smallest. So we come back to our original ICE chart, and because that is the smallest, we can box it, I-box it. Now, the definition of the limiting reactant is the thing that is completely used up in the reaction. So this is going to go, at the end, we are going to have 0 moles of that. Okay, let me see if I can get that thing to focus. So, how much is this going to change by? Well, the only way that this can go to 0 is if we lose, remember we already put the minus in there, if we subtract 0.160 moles, and now that's down to 0. Okay, so now what we can do is take this and we can calculate all the other change boxes based off of this change box. Okay, this is the most important box right there. You get that, the rest of the ICE chart's going to fall into place. So now, in order to convert from moles of this to moles of this, or moles of this to moles of that, or moles of this to moles of that way over here, you have to use an X-line using the balanced chemical equation. So here's how that's going to work. Okay, now I'm going to show you something neat with this. Well, chemically neat, not like go home and tell your family about it, neat, but okay, so we're going to start with the limiting reactant. Moles of NaNO3, and we're going to X-line it. Now when we do this, when we X-line it, notice that I am going to write NaNO3 because we want to get rid of NaNO3 and we want to know how much Ca3PO4 calcium phosphate there is. And when we do that, we're going to use the balanced chemical equation. What's the coefficient of sodium nitrate? It is 6. What is the coefficient of calcium phosphate? it is 1. We look at the balanced chemical equation and we get that figured out. Okay, now before I do the math, let me show you something kind of neat here, because the setup of these problems for all 3 of those boxes is going to be pretty similar. 0.160 moles, remember you have to use the limiting reactant of sodium nitrate, X line, and again we're going to put sodium nitrate on the bottom, but now we want to convert that to moles of calcium nitrate. Okay, and now if we go 0.160 moles of sodium nitrate, we can X line it, and NaNO3 on the bottom, and now sodium phosphate on the top. So now look, all 3 of these based on units are set up almost exactly the same. What's the coefficient for sodium nitrate? 6. What's the coefficient for calcium nitrate? Well, in the problem it was 3. What's the coefficient for sodium phosphate? It's 2. Okay, so I've set up all 3 math problems, and now we can just do the math. This becomes fairly straightforward. So when we do this, divide by 6, we get 0.0267. Okay, and look what's left. Moles. Okay, moles of Ca3PO4. 2 calcium phosphate. Look at what's left. The sodium nitrate cancels, and now we're at 0.0800 moles of hold on 1 second. Sorry about that. Moles of CaNO3 2, and now for this last one, it's 0.160 times 2 divided by 6, and so you get 0.0533 moles of, and again look, so it cancels out, of Na3PO4. I always run out of room whenever I do these things, but you get the idea. So now when we come back here and fill in our ICE chart, well, how many moles of calcium phosphate did we use up? 0.0267 moles. How many moles of calcium nitrate did we use? Well, right there, 0.0800 moles. Okay, and then how much of this did we make? 0.0533 moles. Now, the rest of the ICE chart becomes fairly straightforward. All we have to do is some basic arithmetic. So 0.0288 minus 0.0267, and you get 0.0021. And now this, 0 plus this is fairly straightforward, 0.0800 moles, and this is going to be 0.0533 moles. Now the problem doesn't say to end here, so now the last thing that we have to do is we have to calculate how many grams of everything is left over. So I'm going to do that in light green, and I'm going to do it right down below the box here. So for calcium phosphate, we have 0.0021 moles of calcium phosphate. And again, we X-line it, lots of X-lines, and we're going to go from moles to grams. And so we have 310 right here, 310 grams for every 1 mole. And that's going to equal, let's see, 0.0021 times 310 equals, so this is 0.651 grams. Okay, and now we do the same thing for this one, 0.0800 moles of calcium nitrate. and we X-line it. We want to get rid of moles, and we want to put grams on the top. For every 1 mole, it weighs 164 grams. So 0.0800 times 164, that equals 13.1 grams. Then we do the same thing for this last one, 0.0533 moles of sodium phosphate. We X-line it. We have, for every 1 mole, it's 164 grams. Okay, and so now we do 0.0533 times 164, and so that is equal to 8.74 grams. Now the last thing that I want to do is check this. The law of conservation of mass says that the matter cannot be created nor destroyed. So instead of going through, look, I've spent about 16 minutes getting through this ICE chart, the thing to do is to just take 2 seconds and very quickly do a calculation to see if everything works out. And so the law of conservation of mass said that the initial mass here that I'm boxing in red should equal the ending mass here that I'm boxing in red. So if I take these two values and add them up, 13.6 plus 8.93, I'm going to get 22.53 grams. That's how many grams we've started with. Now if I take these 3 masses and add them up, 0.651 plus 13.1 plus 8.74, we're going to get 22.491 grams. And because of rounding, these aren't exact, but they're close enough for chemistry, and now we have solved our second medium-sized ICE chart.